This top.
Okay. We're going to start. Continuing with maximum and minimum values. Last time we spoke about absolute well, we spoke about all of them, but we did an example with absolute maximums and minimums. So now we're going to. Oh, that's 4.1 probably. So last time we talked about the absolute max and min, which was the largest and the smallest values in some interval, and these were guaranteed to exist if our function was continuous by the extreme value theorem. Now we're going to focus on the local maximums and minimums and how we find those, and how we find those is using the derivative. So let's actually do that. So let's talk about finding local maximums and minimums. There are two main methods. One is called the first derivative test. Second one, the second derivative test. I know, surprising. That was. Both require the original function to be continuous. On an interval around the critical point. So if your function is not continuous, you can't even talk about it. It's not a point if it can't be a max or a min point if it's not a point at all on the graph. So if your graph is not continuous, it doesn't even make sense to talk about this. But in the case that your graph is continuous, we can talk about these two guys as a way of finding the local maximums and minimums. So let me describe the first derivative test to you. So step one is to find the critical points. You might remember from last time, these were the points where f prime equals 0 or undefined. Right? So find all such points on some interval of consideration. If an interval is not given, you're finding it on the entire real line, so you find all such points. Find all the critical points. 2. You're going to plug these points into the first derivative, which is why it's called the first derivative test. And you're going to make a conclusion based on one of these two situations that you can find yourself in. Okay. So again, this interval we're plugging into the first derivative. Let's say I have the point x0, and this is my critical point. Right, so I find a critical point, x0, I'm going to put it on an interval. And what I'm going to do is I'm going to randomly pick two numbers on either side of x0. And I'm going to find the derivative of those guys. So I know the derivative is 0 or undefined at this point, but the original function is defined there. But to the left, I'm going to find a derivative. Now there are a couple of situations that we care about here. If the derivative on this side is positive, and the derivative on this side is negative, then what does that mean your function is doing over here? It's increasing. Right? Positive derivative means it's increasing. Negative derivative means the opposite, it means it's decreasing. So if you find a critical point and your function is continuous there, and on either side immediately of that point, the derivative is positive and changes to negative, you'd have done this. And that tells you that you've had a max. So you're just testing points on an interval. Similarly, if this guy is your critical point, and you pick two random points over here, it doesn't matter which points you pick, as long as you're not interfering with some other critical point. There might be several. But as long as you're on an interval between critical points, you can pick any number you want. And let's suppose here the derivative is negative, but on this side the derivative is positive. That means you're decreasing on this side. You pass through the point, and then you're increasing on that side. That tells you you have a minimum. Now that's it. That's based on a lot of concepts that we already know about derivatives. We're really just putting it together in one main test. So again, we know what it means for derivative to be positive and negative, and when in combination it happens this way, we can obtain a max. If in combination it happens this way, we obtain a min. And due to Fermat's theorem, which we spoke about last time, we know that the point that we would care to test is the critical points, because these are where the local maximums and minimums will possibly happen. Right? But Fermat's theorem didn't tell us the whole story, so we kind of have to do some extra tests to help us out. But that's basically the first derivative test. There's nothing else to do. Right? So in this situation, max, that situation, min. Other situations, neither. Unless the other situation is possibly at an endpoint, in which case we usually won't look at that anyway. So that's the first derivative test. We'll do some examples later, but I just want you to understand the idea. Find the critical points, plot them on an interval, test points on either side, see what the derivative is doing, you can make a conclusion from that. In the second derivative test, you would obviously use the second derivative. And this is basically using what we know about concavity. So 1. Say we are at a point and you would find all critical points. And assuming everyone is defined there, and 2, test in the second derivative. Conclude as follows. All right, so it's a very similar. We don't have to do this because we don't even need the interval. The interval we'll test with concavity. I'll talk about that as well. Let's say x naught is a critical point, and we find the second derivative there. So we know it's a critical point from the beginning, and we're going to plug in the second derivative there. What can you tell me if this guy is greater than 0? What does the second derivative tell you when something is greater than 0? Yeah?
Concave up.
Concave up, right? Second derivative is positive, up, you're feeling positive, you're happy, you're smiling, concave up like a cup, all that stuff. So that means you're shaped like this, right? So what kind of point do you think that would be?
Local min.
So that would be a local minimum. So in the event that you have a critical point, you test the second derivative at that critical point, and the second derivative gives you a positive answer. That means you're shaped like a cup, which means you're a local minimum. If your second derivative returns a negative answer, that means you're shaped like a frown. Second derivative is negative, you're down, you're feeling sad, you're frowning. That's a local minimum, a maximum. Right? If your second derivative is 0, then there's no information from this test. You have to use like the first derivative test or something else. In practice, I rarely use the second derivative test, but I know a lot of people like using it. But you have to find the critical points anyway, and very usually you'd want to know where you're increasing and decreasing. So you'll kind of go through this analysis anyway before you even get to the second derivative. So in general, I don't really do this because I always kind of end up doing that first anyway. But if for some reason you have the second derivative given, you don't care about increasing or decreasing, you can jump right to the second derivative test and figure out where your maximums and minimums are. And that's basically it. Now for examples of these, I think just jumping right into the next section, we'll actually see them in action. Because the next section we're going to do is curve sketching. And for curve sketching, we're going to have to be able to find maximums and minimums anyway. So it's a good, we can apply either of these tests in order to do that. So our handouts for curve sketching, and again, they're on the website if you ever lose the handout.
We already have curve.
I already gave you curve sketching?
Can I have one? I don't know.
Anyone need one?
This is the one we I don't know where we are. The same page. Oh, yeah. You use it.
Yep.
See, this is what happens when I don't do something last minute. Now I repeat stuff.
Did I?
I should procrastinate more. I'm trying to get ahead of time. Let me give them this handout early, then I forgot I did. Oh, it's 4 point. Yeah, we finished everything. There would be examples of us applying this test, but we'll apply it in curve sketching.
Why is this so much?
Wait, 145. Wait, did we just finish 4.1 or 4.2?
That was 4.2.
That was 4.2. That is.
4.1 was related rates.
Right. Okay, so that was 4.2. So 4.2 was absolute maximums and minimums and local maximums and minimums. And it ended with us learning how to find local maximums and minimums. And for examples, because we'll do these in curve sketching anyway, I figured I'd save the examples for the very next section where we're going to do it all at once now. And so we have that curve sketching handout. Again, in this section, there are always a sequence of steps that we're going to go through. This is true for related rates. This is true for optimization. It's true for curve sketching. You always want to do things in the same order. The order is less important here, but I would highly, unless of course, if you're going to use a second derivative, you have to have done the first derivative before. But in general, the order otherwise is not really set in stone, but I would recommend that you do it in this order anyway. I would also recommend that you do it in the same order every time, so that you don't end up in a test thinking, what was I supposed to do next again? It'll be like automatic. You'll do it so many times in the same order, it'll be automatic to you. So so I think it makes sense to do it in this order, and so that's the order in which we're going to do it. I also talk about some common mistakes that students make, which I guess while we're doing examples we will talk about that. And there are also examples at the back that we're going to do. Some of these are maybe slightly too complicated for me to put on a test, but I'll mention what those are anyway. But the idea is we're going to learn how to draw pictures of things again. We're going to go back over graphing that we've done in pre-calculus and sort of fine-tune our technique using ideas of derivatives. And so here are the sequence of steps to go through for curve sketching. Okay. So one, you should note the domain. You want to know where does your function exist? Are there gaps? Are there holes? And this we already learned how to find that, the domain of a function. That was on like test 1. Find the x and y intercepts. So that's kind of something, again, from algebra. Remember how you find the x-intercepts? You said the y equals 0, you solve for the x values. To find the x-intercepts, you said to find the y-intercepts, set the x equals 0, solve for the y values. And another thing that's going to be important for us is asymptotes, right? So some functions don't have asymptotes. For example, polynomials don't have asymptotes, but there are others that do have them, like logarithms have asymptotes. things like 1 over x have asymptotes. So there are some functions that have asymptotes. And there are two kinds that we would care about finding. There are the horizontal kinds and the vertical kinds. To find a horizontal asymptote, you're just taking the limit function. So you're just taking the infinite limits, well, limits at infinity of the function. So let's say your function is doing its thing and it's, say, and let's say it approaches 1 as you go. What you'll realize is happening is that you'll obtain that the limit as x approaches infinity of f of x is equal to 1, right? And that number is going to tell you what you're approaching on a horizontal level, right? If the limit doesn't exist, then it means you're not approaching any horizontal line. So that's kind of like the horizontal asymptotes. Now, what happens here, so this is kind of what happens with a horizontal asymptote. We're going to piece it all together soon. I'm just going over these steps. For the vertical asymptotes, that's kind of like when you have this line here that your function can't touch and it does something like this, or it might do something like that. What you can do is, technically, if this happens at a, you're figuring out that you want to find out where the limit approaches infinity. So if you have f of x approaches a from the left, you get infinity. That's telling you as I'm approaching a from the left side, it's shooting up. So that's going to create a vertical asymptote versus the limit as x approaches a from the right of f of x. In this case, I would get its negative infinity, and that's shooting down. And depending on the function, it might be easy for you to see one or the other. Okay? Another common thing that happens your function will be given as just a quotient of two other functions. And you know that your vertical asymptotes happen when the denominator is 0. Numerator not equals 0 at the same time. Although that's never going to be something you have to worry about. Okay? So it's kind of like this, a vertical asymptote, you'll notice that your function never touches a vertical asymptote. It's possible for a function to touch a horizontal asymptote, not possible to touch a vertical asymptote. It will be a line you cannot touch, which means that your function is undefined at that line. And so common ways to find an undefined function is to, if it's a fraction, it's where the denominator is going to be 0. That's usually where an asymptote will happen. Right? If it's a radical, at the point where you start to hit negatives, that's where the asymptote will happen, and so on and so forth. Okay? So we'll look at that when we do it. So the first thing is you want to find the domain of the function, find the intercepts of the function, find the asymptotes of the function. And we're going to practice all these. I'm really running over this, but we'll practice it. And the asymptotes are usually written as broken lines on the function. Now the next one is you're going to find the intervals of increase, decrease, and the locations of the local maximums and the minimums. Right? That's step 4. Now that is basically you doing the first derivative test, right? You're going to find where it's increasing and decreasing. That means where the first derivative is positive and negative respectively. And if there are any maximums and minimums, meaning the behaviors that I wrote here occur. Then second, you're going to find the intervals of concavity. In other words, you're going to find where's the graph concave up, where is it concave down? And are there any inflection points? Are there any points where it switches from concave up to concave down? That is using the second derivative. And after 6, you sketch the graph. You put all this information together into one big soup and draw the graph. So let's actually run through these steps here. We'll go through a few examples so you see how the steps work together. We'll start with some easy ones, like part A is pretty easy. We actually know what that looks like already, but I just want to graph it again in a more technical fashion so you can go through the steps. So let's look at A. F of x equals 1 over x squared. So you can pretend you forgot what that graph looks like, and for some reason you have to figure out by hand what it looks like. So 1. What you would do is you find the domain of this function. What is the domain of this function?
All real numbers except 0.
Right. So all x in R with x not equal to 0. Or it is defined on this interval. So we know as long as we're not at 0, we're cool. Okay, so you move on to step 2. You will want to find intercepts. So start by finding the x-intercepts. What do you do to find the x-intercepts?
Y.
Set y equals 0 and solve for x. So this means 0 is equal to 1 over x squared. What does that mean? What would x be? Well, x cannot be 0. We can never divide by 0. 0 is not in the domain, so it's impossible. So what's...
So there's no x-intercept?
There's no x-intercept. No solution to this. Means there's no x-intercept. Meaning that your graph does not touch the x-axis, which is fine. What about the y-intercept?
Set x equals
That means you
0.
set x equals 0, solve for y, but this, not in domain. So no y-intercept either. So find the domain, find the intercepts. There happen to be none. Our graph doesn't touch either axis. So what are we going to do now? 3. Asymptotes. Let's focus on the horizontal first. For the horizontal, we're going to find the infinite limits. So I'm going to find the limit as x approaches infinity of our function. I'm going to find the limit as x approaches negative infinity of our function. If either of these give me a constant, give me an answer, that will be the horizontal asymptote. What is the limit as x approaches infinity of this guy?
0.
0. What about as x approaches negative infinity?
0.
It's also 0. Which means y equals 0 is a horizontal asymptote.
Do they have to match, or is it like if you had two different answers?
It turns out for rational functions they will always match, but for other functions they might not. It's possible to have two separate ones, so just check both, just to be sure. Turns out if you have a ratio of polynomials, it'll always be the same, but in general it's not the same. So that's how we find the horizontal. For vertical asymptotes, again this is given as a fraction, so we're pretty much set the denominator equals 0. So this means x squared equals 0, so x equals 0 is your vertical asymptote. So we found the asymptote. So I have a horizontal asymptote, I have a vertical asymptote. Which brings us to step 4. So step 4, you'll realize that we're finding where we're increasing, decreasing, where we're a max, where we're a min. Okay. So now here's where well, we're doing calculus before, but here's where the calculus really comes in. So what we're going to do here is we need to find the derivative, obviously, because that's what tells us about increasing and decreasing. So I'm going to find, if this is my f of x, I need to find the first derivative. And what's that going to be?
Negative 2x. No, negative 2 over x to the negative 30.
Right, because this is, I would think that this is x to the minus 2, so the derivative should be minus 2x to the minus 3, which is that guy. I want to do the first derivative test, so I'm going to locate the critical points, because I'm going to do that. So for critical points, your f prime equals 0 or undefined. This means minus 2 over x cubed equals 0. or minus 2 over x cubed is undefined. This guy, notice, has no solution. This guy, x equals 0. So x equals 0 is the only critical point. And we can remember, a fraction can only be 0 if the numerator is 0, right? So since the numerator is 2, it's never going to have a solution. Now that I found that critical point, what I'm going to do is I'm going to test it on a number line plugging into the first derivative. So I'm going to plot 0, and I'm going to plug in any random number to the left and to the right of 0. So I can pick minus 1 and positive 1. And I'm going to plug that into the derivative. Right? So if I plug that into this guy, plug in minus 1 into 2 minus 2 over x cubed, do I get a positive or a negative answer?
Positive 2.
Right, because I plug in minus 1 here, minus 1 cubed is negative 1, and I'm dividing negative 2 by negative 1, and it ends up being positive, so it's positive here, so I know I'm increasing. Now if I plug in 1 into this, I get a negative number. That means over here, f prime is decreasing. What does that tell me about this point?
It's a local max.
No. Why not?
Oh, because you don't have anything 0.
It's not in domain, right? So, by the way, that means it's not a max, right? This is why step 1 was important, for you to know ahead of time what are the nice points that we can work with. 0 happens to not be a nice point. So while the picture might look like it's going to be a local max, remember the first derivative test only applies as stated if the function is continuous. We're not continuous at 0. So I do know it's increasing here and it's decreasing there, but there is no maximum or minimum because the only candidate for the maximum is actually not in the domain. Let's move on.
So when you get to the x equals 0, can you just stop there? Since you know that that's your only possible critical point to plug in.
No, because we care about where it's increasing and decreasing. So we still want to do this analysis here.
Oh, okay.
Right, because I still want to know when am I moving up versus when am I moving down. So this is going to be important in any way. So it's a matter of, if the question was just to find what is the maximum, then when you get here you can say there is none. But we want more than that. So we do this anyway. Fifth step. We're going to want to figure out concavity and inflections. If you refer back to that table we did a long time ago talking about what the different functions do, you'll realize that to talk about this, you talk about the second derivative. So I know f was, and I'm just rewriting this here, that f prime is this. So f double prime is what?
6x to the negative 4.
Or 6 over x to the 4th. Now, again, I'm going to want to test this in its critical points. So similar to the first derivative, I'm going to do the same thing. So I'm going to set this equal to 0. And set this undefined. This gives us x equals 0. This gives us no solution. So 0 is my only point that I'm going to test around. And I'm testing into the second derivative. So I pick a random point like minus 1. Pick a random point like 1. And what is the sign of the second derivative here? Because this is my function.
Positive.
Positive.
Also positive.
And this, again, positive. It's always positive. What does that mean on this side?
It's concave increasing up.
Concave up. It does not mean increasing. It just means we're shaped like a smiley face. On this side, it tells us the same thing. It's concave up, shaped like a smiley face. Also, we learned that there are no inflection points. right? Because an inflection is when we switch concavity. We never switch concavity. It's always the same concavity. Okay, so copy that all down and we'll put it all together. And again, I know it's overkill for this graph. I just want to illustrate the steps here. But 1 over x squared, we should all know how to draw that by hand, by heart. So what I like to do is all the information I find through these 5 steps, I'm going to put that all on the axes that I'm going to sketch the graph on. So I don't have to be swallowing too much information all at once. So I kind of summarize it on the axes. I can probably put it in here. So now we're in step 6. We're just going to sketch the graph. Now we're going to plot all the things that we found before. Notice there are no intercepts, so we can't plot that. So it didn't touch the x or the y. In future examples, we will actually plot those. But what else do we know? We know that 0 is where the graph is undefined. We also know that's a vertical asymptote. So what you do is, remember for asymptotes, you draw like broken lines. So we realize that along the y-axis, that's the line x equals 0. That's actually an asymptote. And along y equals 0 is also an asymptote. So this broken line is not a part of the graph, it's just something that we're identifying our asymptotes. So I know that I cannot touch this line. I also know that as I go off to infinity, I should be getting closer to this line. What else do we know?
Concavity up on both sides.
Well, go to the next one in the thing would be increasing, right? Where were we increasing?
On the left side of the...
From negative infinity to 0 we were increasing. Okay. So how I like to do that is like towards the bottom of my graph very faintly, I'd like write this and I can like write a starting point and go back and I'd write a little increasing right there. So I know that in this region I should be, whatever my picture is doing, it should be moving up as I'm going from left to right. Over here, I know I should be decreasing. So I put a little labeling on the bottom. What else did we know? There was no max or min, so I can't plot those. So we move on to the next thing, which is concavity. I know I'm concave up everywhere over here, concave up everywhere over there. So I'll put another little line, concave up. Another little line here, concave up. So now I'm in this situation. Right? I know that I'm going to draw a picture that is increasing and concave up on this side, and it is also decreasing and concave up on this side. So let's start with this side, and you'll kind of see why. You'll build some more intuition with more examples. But what would the graph have to look like here?
Like that.
Could I be down here?
No,
And why is that?
because it's concave up and it's supposed to be decreasing.
But I can draw it concave up and decreasing. What would be the problem with
It's
doing
going to
that?
run into the axis.
There's no problem with running into a horizontal asymptote. I could do that. Why is that still wrong?
There's no x-axis.
Because what?
There's no x-axis.
Right. So now if you're drawing this, and I mentioned this in the paragraph at the bottom, you have to make sure that you're falling in line with all the information you had before. You know there's no x-intercept, so there's nowhere your graph could be underneath here, because to go to the vertical asymptote, it will have to cross the x-axis, and there's no x-intercept. It's also true that if I started here and I kept decreasing, which I should always be decreasing, I'll never actually get back to the horizontal asymptote. my graph should be leveling off at 0 as I go to infinity. That's not going to happen if I'm down here. So it means that my graph must be up here. So I know I must be up here the whole time. I can never actually cross the axis. So I know my entire graph is in the first quadrant. Then I know I should be decreasing and concave up. So I should be going down as I move from left to right, and I should be shaped like a smiley face while I'm doing that. So I know my graph should look like this in this region. Also know that I'm leveling off at y equals 0, so I should go like this, and I never touch the x-axis and I never cross it. But also this is a vertical asymptote, I can't touch that either, so I should be approaching that as well. And so my graph ends up looking like this. Which falls in line with what we knew all along. A similar consideration happens over here. You say, can the graph be here? Your answer would be no, because I should be increasing, and that would create an x-intercept, which I know does not exist. So the graphs have to be up here. And for the same reason, it would have to be like that. Going up as I move from left to right, because it's increasing, and it's shaped like a smiley face. And the horizontal asymptote is 0 as I'm approaching here. So I end up with this as the picture. Let's do another example. It's something you have to get used to. Move on to part B. A little bit more complicated, but it's still a polynomial, so it shouldn't be too crazy. Did we already have this? So we're going to do this guy, B. F of x equals x to the 4th minus 4x squared. By the way, on the test, there's just going to be like one massive curve sketching problem. There's just going to be one problem that says find all these things and sketch the curve, and it's going to be like one 20-point problem, or maybe 25 points or something like that, where I'll give you points for each section that you do, and then for the picture. So you will have to go through this entire process at some point. So let's actually go through it, run through it a couple of times so we get used to doing it. Right? And it's very important that you pay attention to your information and the picture. They have to match up. If in your information it says there's no x-intercept, but you draw a picture that has an x-intercept, something is wrong somewhere, right? Don't forget, right? Don't be like a goldfish and forget what you did. It's very important. So the first thing we do is the domain.
All real numbers.
All real numbers, a polynomial. So I know there's no bad points. Everything is permissible. So 2, now we're going to find the intercepts. Let's start with the x-intercept. This means I'm going to set y equals 0, and I'm going to solve for x. How do I solve that equation?
You pull out the x squared.
X squared is a common term.
And then
X plus 2x.
Alright, so that's x minus 2, x plus 2.
it's 0 to -2.
Don't you miss those days? It was like, where all you had to worry about was solving this kind of equation. It was like, man, that was so difficult. Now it's like, this is just like one step in like a multi-step thing now. So you get 3 guys. 0, 2, minus 2. There are 3 x-intercepts, which means when you draw that picture, you must have 3 x-intercepts. Not more, not less. 3. Okay. Y-intercept. This is when you set x equals 0. Okay.
0.
So this means y equals 0. Right? Which makes sense. If x equals 0, that happens when y equals 0 at the same time on the Cartesian axis.
What?
Right, x and y equals,
Wait, what?
like in the xy plane, x and y are always 0 at the same time.
What's the Cartesian?
That's what it's called.
What? The xy plane is called the Cartesian axis.
Nice.
Did I never use that name before?
No.
Okay.
Wait, what time is it?
What is that? It's 1.
1:40.
So you're leaving at 1:30, right?
I was gonna. Okay. No. I'm leaving now, actually.
She's gonna miss the good stuff.
Yeah.
Now it gets interesting.
I'll
Gonna be sorry.
I'll watch the video.
Okay, shut it down.
Block
you from the service.
Just like block this email. Okay, so
Oh, do you want my homework?
for
Probably not, but-
which one? One is this?
The 2 after the test. It was like.
Oh. Let's continue. So we have so we found the intercepts. What was the next thing? The asymptotes. Now the thing is, you realize this is a polynomial. That's actually great. There are none, right? Polynomials don't have asymptotes. There's no vertical asymptote because I can touch any x value I want, and there's also no horizontal asymptote because if I take the limit as I go to infinity, I get infinity. Right? So there's no HA since as I approach infinity of our function, I get infinity, and as I approach negative infinity of our function, I also get infinity. But the fact that we don't get a number is a problem, right? It has to level off at a number to be a horizontal asymptote. And there's no vertical asymptote since the domain is all real numbers, right? There's no x value that I have to avoid. So, but you can just say non-polynomial and that will be fine.
If we're given the polynomial.
If you're given a polynomial, you can write this.
Yeah, okay, so we don't have to just show.
You don't have to.
Say it's polynomial.
By the time we get to the test, I'll assume, I think you shifted this here. By the time we get to the test, I'll assume you know that how polynomials are nice. Like they're always defined, there's no asymptotes, there's no gaps. They're very nice ones. So you can just write none because it's a polynomial and that's fine. Moving on. Fourth thing. Increasing, decreasing, maximums, minimums. Right, we find all 4 things together because they all come from the first derivative. So what we're going to do is we're going to find f prime. What is f prime here? Now we need to find critical points. Right, so you said f prime equals 0 or undefined. And again, for a polynomial, f prime is never going to be undefined, so there's no solution here. And here we're going to have 4x cubed minus 8x equals 0. How do I solve that? I can factor out of 4. In fact, I can factor out of 4x. So I get x equals 0, x equals radical 2, x equals minus radical 2. So there are 3 critical points here. And I'm going to test those in the first derivative. So I'm going to plot 0, I'm going to plot radical 2 minus, plot radical 2 positive. And you're going to pick random numbers in between all of these guys. So in here, minus 1 is in here, 1 is in here, 2 is over here, and minus 2 is over here, so I'm going to pick those numbers. And you can always use your calculator and plug in radical 2, you realize it's 1.4 or something. And so that's how I know that it's between 1 and 2. So now we're plugging into the second derivative, the first derivative. So we're looking at this expression, which it's much nicer to actually put it in the fully factored form. So if I plug in a negative 1, this is negative, this is negative, this is positive, right? So x would be a negative. Here I have minus 1 minus radical 2, that's also a negative, so negative times negative, which is a positive. Plug in minus 1 here, that's a positive. So it's positive, so my derivative is positive here, which means I should be increasing here. If I plug in 1, that's positive. This is negative. This is positive. So over here, it's negative. That means I should be decreasing here. If I plug in 2, that's positive, positive, positive. It's all positive. My derivative is positive, so that's increasing here. If I plug in minus 2, that's negative, negative, and negative. That means it's decreasing here. Now let's summarize it. So in step 4, what we get where are we increasing? Where are we decreasing? Where do we have maximums? Where do we have minimums? Tell me the interval of increase. We're increasing here, and we're increasing here. So I can write that down as minus radical 2 to 0, union radical 2 to infinity. Because I'm increasing in these two intervals. If I'm decreasing here, here. That's where I'm decreasing. Where do we hit a maximum, if anywhere?
At 0.
At 0. When x equals 0, the function is defined there, so it's continuous. I'm increasing on the left, decreasing on the right, and I hit my tangent line is 0 here, so that actually gives me a maximum. So at x equals 0, which means at the point 0, 0 is a maximum. And where do I hit minimums? At these two guys, because I'm decreasing, then increasing, decreasing, then increasing. So minimum occurs at minus radical 2 and positive radical 2. What are the y values here?
0.
What was our function? What was the original? I forgot. Minus 4x squared. Okay, so if I plug in, now whether I plug in the negative or the positive is not going to matter because all the powers are even. So let's just plug in the positive. This is radical 2 to the 4th minus radical 2 squared. So radical 2 squared is just 2, so that's minus 8. And if I take radical 2 to the 4th, that would be 4. That's minus 4. So this is the summary from step 4. So you write that down and you save it. Move on to step 5. In step 5, we look for concavity and inflection. So, what was the original? Was x to the 4th minus 4x squared. The first derivative was 4x cubed minus 8x. So I'm going to go to the second derivative. 12x squared minus 8. So the second derivative equals 0 or undefined because I want to find the points I want to test. 12x squared minus 8 equals 0. That was the original function.
Yeah.
Okay. And it's always defined, so there's no switch for the undefined case. What can I do here?
Take out 4.
Factor out of 4. And what would that look like?
Times 3x squared minus 2.
So that's going to be a weird number. X would be 2 over 3, and I'm taking the radical of that. So I can test that on the lines. 2/3. Thirds, this is negative. Plugging a point in between here, 0 is clearly in between there. 2/3 is less than 1. If I take a radical, it's still less than 1, so 1 is definitely over here, and 1 is definitely over there. And now I'm going to plug each of these points into the second derivative. So if I plug in 0 here, clearly I get a negative. So here my second derivative is negative. And what does that mean? Concave down. It means down like a frown. So my graph should be have that shape. If I plug in 1 into this guy, or that guy, that's 3 minus 2, which is positive 1, times 4, it stays positive. So over here I'm concave up. And of course when I plug in a negative 1, because it's squared, it gives me the same thing. So right here I'm concave up. So now I can actually summarize. Where am I concave up? Where am I concave down? Where are my inflections? Where am I concave up? On these two intervals here. Where am I concave down? In between those. Where are my inflections? Each of these, right? Here's where I switch from concave up to concave up to concave down. Here I switch from concave down to concave up. So each of these individually is an inflection. And I mean, you'd have your calculator at this point, but they'll both give us the same answer, so we just have to find it once. Minus 4 times this squared. What is that y value? So this will give you 4 over 9 squared. So that would give you 8 over 9. That would be minus 4 over 9. Now we can put it all together. Let's see what we actually have. Remember these points, because I'm not going to remember. Let's see the picture that is revealed to us. Should I take the entire board? So now we have a lot more things to plot. Okay, so start from the beginning and we're going to work our way down. We know the domain is everything, so we don't have to worry about asymptotes. Next thing was intercepts. What were the intercepts?
X equals 0.
0, 2, and negative 0.
Right, so there was one at 0, so I would just draw a point. Right, so actually plot these points on your picture. It should be kind of equally spaced out. So move down a step, there were no asymptotes, move down again. Where were we increasing?
Negative root 2, 0.
So if I put like radical 2 here, negative, and put like radical 2 here. So from here to where?
Negative root 2 to 0.
Negative root 2 to 0.
Was increasing.
Okay, so I'm going to draw a little like here and right, increasing. Where else was increasing?
Root 2 to infinity.
And then from here all the way onwards, I'm also increasing. And we were decreasing everywhere else, right? So we're decreasing here, and we're decreasing here. Did I have a max or a min?
0 is not a max.
So this guy was a max, so we can just label that very faintly. Any mins?
Negative root 2, negative 4, and root 2, negative 4.
So I can have here and here. I'm going to plot these points. What was the y value?
Negative 4.
Negative 4. So I know that these guys are minimums. They're local minimums, so when I zoom in, no one should be lower than. Move on to the next step. What information do we have from that?
Concavity.
Okay, what's the concavity? Oh, well, we have it here. So there's going to be another one. So I'm going to plug in a number here, call that minus radical 2/3. Call this positive radical 2/3. And the concavity was from this guy, these guys broke up the concavity, so what was it? So we were concave down in between them. So from here to here, we're concave down, and we were concave up outside. And we also had inflection points here and here. So I'll just call a point over here, -4/9. Plot that, that's an inflection, INF. Plot that, that's an inflection, INF. So now I have all this and massive amounts of information plotted on this graph. And it's a 4th degree polynomial, so it'll have a lot of information for us. And now I want to just draw a picture that does all these properties. I know that these points are points that my graph should be passing through. They're all points on the graphs and they mean something. I know this is a minimum, so my graph should look like this, passing through it. This is a maximum, so my graph should look like this, passing through it. Graph should look like this. So now we go in one interval at a time and see what's going on. So in this interval here, right, this is where the break happens. Notice here I'm decreasing and I'm concave up in this region here. So I should be decreasing, but I'm shaped like a smiley face. And so my picture is going to look like this. It's coming down and it's kind of bent outwards. It's concave up. Now I move in between the next break. Here, I'm still concave up the whole time, but now I start increasing. So now I'm going to increase concave up. So I'm concave up this whole time. I'm shaped like a smiley face. But over here, I'm decreasing while concave up. In between here, I'm increasing while concave up. Move on to the next region. Now I'm in the region where I'm still increasing the whole time, but I switch the concave down at this point. So at this point, my concavity is going to switch to a frowny face. That's shaped like a frown, that's shaped like a cup. Moving between this point, I'm decreasing concave down. So I'm decreasing, but I'm shaped like a frowny face. Sorry about that. Still decreasing, but now I switch the concave up. So I'm decreasing like this. Now I'm increasing and concave up. So that's my graph, it's a W. So this is the graph y equals x to the fourth minus 4x squared. Now that is something that we could have graphed since pre-calc, but it's not something we could graph in this level of detail. You could, in pre-calc, you couldn't tell when a certain bend was happening, but now we can tell exactly what coordinates the bends are going to happen and how the bends are going to behave. So notice here, I'm decreasing in concave up. Over here, I'm increasing in concave up, increasing in concave down, decreasing in concave down. Here I'm decreasing in concave up, and here I'm increasing in concave up. Yeah.
On the exam, are you going to want us to put all, like, write down the intervals of concave up, increasing, all that stuff, or is it okay if we did the work beforehand and then just sketch the graph based on that information?
I think it'll be easier for you to write that out, but I don't particularly
But it's not
care
necessary?
if you need it. What I would care about is that the points that the graph is passing through, that you're plotting those.
Yeah.
Like that those are important to write.
Mm-hmm.
These guys are kind of just like a skeleton to kind of guide you as to what you're trying to do. What time is it?
2:11.
I think my watch is broken. Do we stop at 2:15, right?
Yeah.
Okay, so we'll stop.